That seems to work.
Welcome to the Building Git Book Club. We're going to cover chapter 6 today, and Katrine has very generously offered to host it today. So please take it away, Katrine.
Yeah, thanks. I wanted to host this chapter because for some very simple reason, it's almost my favorite feature in Git, and that's the one that helped me basically get started with it, because I'm from a university background, so I worked there for a while, and wanted to start using LaTeX for work. And this workflow of writing something in the text editor, then switching to some other kind of rendered version, whatever that was, like a PDF or so, was totally normal to me at this point. And it seemed to me that Git provides the same thing with this adding and index and cache feature. So, and because I used usually some graphical clients back then, it was always a nice different view to what I had just written. So this back and forth was kind of normal, except we didn't have commits back then. So that's only what Git provided then in the end. The index, therefore, is a kind of a tool to help you review your own work or the work of others if you pair program before deciding how to actually comment it with a Git message, commit message, and commit it into the actual version control system. Did previous version control systems, by the way, have a similar concept, or was that one of Git's innovation? I only started with Git.
I'm trying to remember actually how the only thing I remember is, like what was the ones we used to use? There was always this common server, and you had to synchronize. You had to get the whole. Everyone had to get a copy of. I've forgotten how it works exactly, but I also don't remember what happened with commits. They must have had some concept like commits. I'm going to just. Yeah, now it's coming back to me. Yeah, Mercurial, Bazaar. I remember Bazaar, actually. I hated it. Yeah, so how did that work exactly? It's amazing how I've completely forgotten it. Well, all of them were inferior to Git, put it that way, which is probably why we're here today.
Well, I'm happy that I jumped into onto the right horse then at the right time. All right. Yeah, let's dive in. I'm gonna share my screen to the PDF. There we go. Oh, there's probably a lot I need to get out of the way here. Okay. Yeah. And yeah, as in the previous chapters, we start here as well by using Git itself to create a little dummy project and an example file and example commits. And Mr. Hoagland here then shows us and explains to us how the index data structure or the index file is actually composed. Again, we do the hex dump, and for some of these aspects, we will probably see the same as for blobs, but a few important differences are that the header starts out with a very peculiar signature, I guess you would call it. So DIRC for dir cache, and version number, and the number of entries is at the start of this header. And then we have a whole batch of file system statistics related to the entries we have added to the index. So we see the ctime, mtime, and so on, inode, and the user and group ID, which we discussed in the last chapter as being essentially ignored in the end when we actually commit something. But here in the index, they are still used. Then the individual files and the file names and the hashes of the files are included as well. And the index itself then is hashed as itself as again. And that's what the last few bytes basically are here approximately. So therefore, some of the concepts that we've seen with commits are the same here, but a few are also specific to the index. Does anybody find a particular data field here noteworthy? Or even not noteworthy and is wondering why it's included at all?
Yeah. In fact, sorry, I have something that's noteworthy on the previous page.
Okay.
If we just go back one, yeah, this bit where I found this quite interesting, where it's possible to have the same file. I guess it's obvious, but there's an example here where file.txt is added as an empty file, and so it's so this was a bit of a light bulb moment to me about it's now, once you do the add, it's now in the index already. And then we add something to file.txt, and essentially there's now two different versions of the same file in the I mean, obviously that's obvious, but it just did a bit of a light bulb for me, that particular example.
And yeah, in day-to-day work, I also noticed that this happens quite often, that you already added something, but then you went back to change something more and have to re-edit again. Yeah, that's yeah. So I always thought of it as a left to right workflow, basically, with staging area as a almost physical space where you can review the changes. So yeah, it always seemed pretty useful to me to have these 3 steps: working directory, index, and commit, with possibly 3 different states at the same time. Okay.
Actually, just one thing from me. So when I was running this, I did actually run into an interesting issue here. So there is a feature in Git called the untracked cache. So that's something you can set in your Git config, and it's supposed to speed up doing actions on your index. So somebody had shared with me that quite a while ago to set it as a Git config, but it then meant that this hex dump was completely different. It did take me quite a bit of time to figure out. So yeah, it's just a feature called untracked cache. It might be in your Git config for anybody who might be watching this and is seeing output that looks different to this that you're seeing in the book.
All right, interesting. So it modifies the structure of the index itself,
or
some other.
It's a feature basically that does some extra, I guess, enhancements or whatever, just to speed up anything on files in your index, I guess. So.
So if everything is different, maybe it's a different algorithm for, I don't know, compressing or fingerprinting or something?
Yeah, perhaps, yeah. I'm not quite sure the exact specific implementation, but
cool.
It's so big, Git. You don't realize how big it is, actually. Like, it's actually a collection of utilities.
All right. Okay, thanks for sharing. Let's add that to the doc. I'd be interested. I mean, luckily I don't work with large files too often. So, but yeah, one already very interesting thing I found out in this chapter, which I didn't fully realize before, is that the adding is already the command that does all the heavy lifting in terms of hashing and creating the blob files also. So that then the commit procedure is actually just a fast generation of this commit object, and therefore the linking to the parent commit and so on. So that's something I didn't really know before, but it totally makes sense. Yeah, to do the heavy lifting early in the workflow when it's a manual workflow. Okay, anything else we should discuss about the specific structure of the index and the hex dump? I mean, probably it was quite fun to keep comparing it when writing the book and writing the code in Ruby.
Yeah, hex dumps just make my eyes glaze over in general. So I have to really struggle to read this stuff.
Yeah. Okay, so sorry, I've printed out here. That's why maybe hearing some annoying noises. What did I want to talk about next? Yeah, I think we can go to the basic add implementation. And the idea here is basically to start with a simpler version and then go to a bit more complicated version later. And the simple version basically keeps the workflow that something that's committed is taken directly from the working directory, and the add command is just added as a parallel thing, basically. And later, and as Git itself does it as well, we want to change the commit command to take only what was added and just commit that. So it's a 3-step process eventually, but right now it's basically just the working directory and adding and committing as a separate thing. And in the JIT main file here, we therefore include the whole block of the add command. And again, most of that is relatively similar to the committing. So the root path, git path, workspace database, operations, all of that is essentially the same. And only the here the file system, stats, and the index related things are actually different. We also reuse the concept of the entries for the different directories and files and so on, with one important detail at the very first, at the beginning, so present, and that is that we can only operate on a single file so far. And we're going to change that later in order to first operate on multiple files and then also operate on directories and recurse into them to find the files automatically. But first we create the index class as well here. There is, again, we see this pattern of using a few constants here for the mode, and then this whole batch of different statistics fields basically gets added and packaged, relatively boringly into a struct that, encapsulates it according to the definition of the index file format. I guess there's not many very interesting things about this to discuss, or are there?
I just want to. I really admire the quality of the code in this book. Like the attention has gone into layout, and like like this is just such a readable little class, and also this I kind of like the this inlining of the struct where it's struct new and then we just got a block. Which is pretty kind of cool way, I think, of doing things. So, and just throughout the whole book, there's just some really good code practices in general. I think we mentioned that last time with using the C constants for file opening, which we don't typically do at GitLab. But okay, yep, that was all I wanted to say.
Okay, thanks. Yeah. Good. Okay, so even if the code itself is boring, we can admire the layout. Awesome. Then I think the maybe procedurally next more interesting approach here is the updating of the index, because we reuse the same log file pattern essentially. First checking whether there is a log file already so that we can ensure that only a single process at the same time writes to the file. And the write operation is also structured into multiple parts. So when we begin the write, we, for example, start generating the fingerprint for the whole index file. Then we write the header. We write each of the entries individually. And interestingly, then the fingerprint or the digest is updated continuously in so-called rolling hashing, which presumably makes the whole thing a little bit more efficient, so that by the end, when the writing is finished, this hash is already present and not the same file has to be fingerprinted again, presumably. Or can anybody correct my presumption there?
I think that's right.
Good to know. So that also would mean that there are probably some hashing function which can't do this kind of rolling mechanism, and therefore Git is limited to a particular type of hashing.
I think we discussed earlier that how we're just using SHA-1, but then there's been this effort to bring in SHA-256, I think it is, but that's actually a big can of worms, and it's not compatible with SHA-1 hashing. So but we discussed that last week, I think, or the week before.
Okay.
But SHA-1's where it's at with Git, really. Yeah.
And works reasonably well. Cool.
One thing I did notice actually, I was a little bit curious as to why in this case we sort of just use the lock files before writing the index, whereas previously when we've been doing blobs, we had used the temporary directories. So I was a little bit curious as to why we didn't use the same type of a mechanism there, or I guess is it just because it's in memory and it's not in the disk, or I didn't quite fully capture as to why we didn't use the exact same mechanism as when we were using blobs.
I was thinking of the head file, actually. That's where the log file was used, right? But the question is valid. I'm not sure about the answer, to be honest.
I would take a guess in that, the index is basically relatively small, whereas the blobs can be massive. Yeah, it'd also be an interesting question whether it's implemented in the same way in Git itself, because this is purported to be faithful to the C code, but yeah, who knows?
But even a big blob would pass through the index, wouldn't it, when it's added?
Yes, but is it hashed separate? Good question.
Can somebody note it down in the doc, please? Then maybe we can look it up afterwards. Okay, let's focus on the individual entries. Again, Mr. Hoagland here was kind enough to construct or look up this cryptic entry format that needs to be used in order to match the Git index specifications. And then when the data is serialized, we also have here this padding with null bytes until we reach a size that is a multiple of 8. Therefore, here the modulo operation. Before the data is then actually written into the index file. And going back to this original little test with Git itself, here we can see that the implementation at this point produces the exact same hex dump output or the byte compatible file, unless this untrack kind of option was used. So that's interesting to research for later. And yeah, I mean, this is, to me at least, not being a programmer, this is where the magic apparently happens. But it's good to know there's just a few pages of code and not actual magic. Next, we want to start storing multiple entries. At first, and yeah, I find it cool that in this chapter, but also in the earlier ones, there's often let's say a sequence of a simple step and another simple step and maybe a third one in the end to achieve a relatively comfortable user interface, and accepting, for example, helper tools here like find as the intermediate steps, so that at each step we have very little code changes, which is super useful for understanding. But at the end of a chapter, we still reach a quality of the user interface that would be comparable, I would say, to Git itself. So that's just a really good style of writing and explaining.
The author subscribes to the GitLab value of iteration.
Yeah, certainly. Except that maybe they didn't publish each individual iteration for feedback, maybe. Or I'm not sure, how old is this book? I mean, was it maybe written on LeanPub or one of those platforms?
Yeah, so it was on LeanPub or something like that, and it was published.
It was cool.
Yeah, published in 2000. No, sorry, that's not correct. Actually, sorry, he hosts it directly on his own website.
All right.
And it's self-published, so there's not a paper copy available, and it was published in 2019, and there's since been a couple of updates to it, but nothing substantial.
Okay.
It does
still,
come.
I mean, it's
go ahead.
iterating when learning.
Yeah, it does come with a copy of the code as well. And if you check through the commit history, you can sort of see each of these chapters step by step. So if I got lost in a couple of places, so it's useful to be able to just step in and see what the code is supposed to be looking like somewhere.
And the code's been pushed up to the book club repo, by the way. I'm not sure if I made that clear. I had a vision at one point of trying to find which commit matched which chapter, but that looked a bit hard.
Yeah, I've also tried learning in the diffs for a while, and then to add all the explanations or the summary of explanations to it, but it's not an easy format to work with on a day-to-day basis. So yeah, this literal programming kind of approach with the code listings in between the explanations is time tested and probably best. Cool. Yeah, back to storing multiple entries. As we have currently the situation here is that the only the first argument is being used, and that has to be a file. And therefore this whole block is basically turned into a loop, so that we iterate over each of the arguments in order to perform the same operation with the file statting and the reading and the writing of the blob and so on each file. And in the next part, we come to a data structure related insight. I wasn't aware of this, but the Ruby language does not have a guarantee that the entries in a hash are output or iterated over in a specific order or always in the same order. And therefore, to be compatible with the Git hashing, which in turn relies on the exact same order of the path names to be fixed and always repetitive, we need to switch some part of the code to a so-called sorted set, where these guarantees are given by the Ruby language. And the approach that the author here chooses is that the keys, meaning the path names of the entries, they will be stored in a sorted set, and then we iterate over each of the entries in the sorted set in order to then retrieve the values for these keys from the entries, which is a hash where we don't have this sorting guarantee. And yeah, by that layer of indirection, we can ensure that in the end, the hashing always encounters the same ordered set, basically. Did I understand this correctly? Because this honestly was the part where I
Absolutely. No, you absolutely nailed it. It's
okay, thanks.
yeah, it's the same in Python, actually. The dictionary is not guaranteed to be in any order. And so there's a different, I think there's a different data type in Python as well, sorted dictionary or something. Yeah.
I find this a little bit weird because in my experience with a little bit of Python for data analysis, nothing really fancy, and a little bit of Ruby scripting for little tools, I noticed that I quite often need to have stuff sorted. So why don't these languages provide that in the simpler data types already?
I imagine it's an overhead with keeping it sorted. And, you know, if you don't need to have your dictionaries, you know, most of the time you access the dictionary by key. So yeah, if you don't need it, why add it, you know, to processing time? Because, you know, any time you'd add something to the what am I saying, dictionary? What's it called? And to the hash, you know, you'd have to resort it every time or remove something.
Okay.
Yeah.
I guess I
guessing.
wasn't doing lots of operations that add stuff to hashes, maybe. Okay.
Yeah, technically as well, I guess a hash doesn't have to have a string or a number as the key. It could be any data type, and when you've got a random data type, you're going to then have to define the sorting for said thing as well. So
okay, so performance-wise, it would also only really make sense to use the sorted type or sorted set here for something that is actually easily sorted, like string.
Or something that you can define a sorting rule for. So
okay. Okay. Right. Okay. Thank you. Yeah, so we have that. And I think that's almost my last note I made. And yeah, so we're at the second to last step, basically. We can now use an external helper tool here like find to input lots of files at the same time. And our JIT will then write the index entries for each of them always in the same order. And then when we commit, it would also do the same thing. But we want to get rid of this external helper, and therefore we want to be able to have JIT detect whether some argument that we pass in is a folder or a file itself, and then behave differently. And in order to not break the behavior for the case where no argument is being input, we basically go to here the list file method and start requesting an argument, but we will set it to the path name, which at this point by default is always the working directory. So if list files is called just like that, it will go through the entire thing. And yeah, we introduced this if else branches here basically, and in the case where only a single file is being input, then we return this as a basically a single element array. And in the case of a directory, we keep this recursive approach and generate an array of all the paths so that the data type in each case remains the same. And in the end, therefore, we have basically the workflow here in our add command that a path name that starts out as being absolute is basically iterated through, and for each path name that is then relative, the operation of adding it to the index is performed, as we saw in the hex dump in the very beginning. That's all I've got.
Yeah, no, Katrina, you made a great point about being in the root directory of the project, because like if you've ever, well, I'm sure everyone's done it, where you happen to be down in a subfolder inside your project, and then you add it, it acts in a weird way. I've forgotten what it does exactly, but it doesn't actually add properly, right? Anyone help me on that?
If you do a git add dot, it adds all files in this directory and subdirectories, but of course if you want to commit something in a parent directory, it wouldn't work.
That's right, exactly. Yeah, thank you, John.
Okay.
Yep. So yeah, I've made that mistake numerous times actually, and then you need to undo the commit. Yeah, Katrine, that was so awesome. Thank you so much for running that today.
Thank you.
And I think that's actually a great place to stop there. And anyone else got any closing thoughts? Any volunteers to run it next time? I'm happy to do it. Great. Okay. Well, thank you so much, Katrine. I'll stop the recording somewhere, and I'll post that.